Welcome to my talk about Bluetooth Low Energy testing with combinatorial methods. My name is Dominik Schreiber and my colleagues are Dimitris, Simos, Manuel, Leithner and Jovan Zivanovic. We are part of the Dimitris research group at SBA Research and work on bridging the gap between mathematical foundations and software testing. To this end, we research and develop combinatorial methods for software and software security testing. So combinatorial testing, or CT for short, is based on an empirical observation by NIST that most software errors are triggered by a low number of parameter interactions, most of the time 1 to 2. Combinatorial security testing, or CST, is an extension of CT with the goal of applying combinatorial testing methods to the field of security testing. The main difference between the two is how the input models are created and the kind of errors that the oracles are trying to detect. While traditional CT mostly includes valid and well-formed inputs in the model, CST focuses on specifically crafted inputs like long strings or strings with specific meaning, with the goal to trigger vulnerabilities and unspecified behavior. In the past, CST was successfully applied to test software for SQL injections, cross-site scriptings, and TLS implementation issues. As can be seen in the diagram, the CST flow starts by thinking about what kind of attacks the target could be vulnerable to. Following that, an input parameter model, or IPM for short, is devised with parameters and possible values for the parameters. Using the IPM, a covering array generation tool can be used to generate a test set that can be executed then against the target. After a test is executed, an oracle checks if the target behaved as expected or if an error was triggered, which is then logged for further analysis. Here we see an example of a covering array, or CA for short, which is a structure that is used in CT. CA provides T-way parameter interaction coverage guarantees regarding the input model according to a chosen interaction strength T, which is often more desirable than probability-based input mutations used by most fuzzers, which provides no coverage guarantees. The input model in this example consists of 10 parameters, each having 2 possible values. An exhaustive testing approach in this case would need to execute 1024 tests. But if we know, for example, that there is a maximum of 3-way parameter interactions that trigger a fault, we can cover all 3-way parameter interactions with only 13 tests, as we can see here in the CA. As can be seen from the image, every combination of 3 parameters cover all possible value combinations of the parameters. The colored regions are basically examples where we see that these groups cover all possible value combinations, but this counts for all 3 parameter groups of these parameters. The whole CA represents basically a test set, with every row in the CA being a test case. The problem of optimal CA generation is believed to be NP-hard, but there are various tools implementing greedy algorithms which can generate relatively small CAs in a short amount of time, also for large input parameter models. So we built our testing method on the Greyhound fuzzer, which was presented a couple of years ago at this conference, actually. It was initially built for Wi-Fi testing, but got extended to also support Bluetooth Classic and Bluetooth Low Energy. The developers of the framework used the SCAPI packet manipulation library and extended it with definitions for all layers of the BLE protocol, Bluetooth Low Energy. This allows to manipulate all fields of a BLE packet and therefore the testing of all layers, including the link layer, which is often not tested because it was difficult in previous frameworks. To send the packet over the air, the Greyhound fuzzers the Greyhound developers implemented a custom firmware for the NRF 52840 dongle, which is actually capable of sending arbitrary BLE packets, and it can be controlled by sending commands over a USB serial connection to the dongle. Additionally, they added a state machine for BLE, which is shown here on the right, which can initiate a connection to a peripheral device and also respond to received packets. The state machine is depicted here and represents all states of an interaction between a master and the peripheral BLE device. It starts with the initial advertisement sent by a peripheral and ends in the disconnection state. The states in the orange part can be traversed in any order depending on the BLE implementation of the peripheral. The fuzzing component of Greyhound traverses the state machine guided by probability and manipulates the values of BLE packets, again guided by probability, with the probability values being optimized by a heuristic optimization algorithm to maximize the triggering of unspecified behavior. For more details about this, I refer to the original paper of the Greyhound fuzzer. For modeling the input space, we regard BLE packets as composite systems consisting of individual layers that are then modeled as subcomponents. An example of a BLE connection request packet and its layers is shown on the bottom left here, consisting of 3 different layers. So in the end, we devised one model per layer. An example of an input parameter model for a connection request layer is shown here on the right. The possible values for the model were chosen by analyzing the Bluetooth specification and looking at data types of the respective fields as defined in the SCAPI packet definitions. Additionally, we also added keywords like unchanged, larger, and smaller to some values, which specifies that a value should remain unchanged, increment, or decremented, respectively. To avoid the occurrence of too many invalid values in a single test case, which could lead to tests being rejected too early by the target, we marked invalid values with the tilde symbol. This way, some CA generation tools, like PICT, for example, can be configured to only allow the occurrence of a single invalid value per test. As already mentioned, we regard BLE packets as composite systems. There's one model for every layer, which is then used to generate one CA of strength 2 for each layer. Since we also want to test interactions between the layers, the layer CAs are combined to a meta CA, again of strength 2. The layer CAs are used as parameters of the meta CA, with the rows of the layer CAs being the values. As can be seen on the right, every column of the meta CA corresponds to a layer, and every row of a layer CA corresponds to a value in the respective column of the meta CA. Now a quick overview of our combinatorial security testing strategy. To make the traversal more deterministic, we started by creating a set of all possible paths to all states. The testing loop then selects one of those paths. At the last state of the path, we then check the structure of the BLE packet that is about to be sent and generate a meta CA with the method as described before. For every row in the meta CA, we traverse the path to the last state, in which we then replace the values of the packet field with the ones from the current meta CA row. This altered packet is then sent to the peripheral, followed by normal packets until we disconnect, which marks the end of a single test, and we record the oracle results together with information about the test case that we save to a database. When all meta CA rows have been used and no new packet is discovered in the current state, the next path is chosen until the path set is completely empty, which then means we have tested all states with all possible paths to them. Then to clarify the test execution, we have an additional diagram showing the execution of a single test case. Assuming we have chosen a path to the state feature request, we start by sending normal packets until we have reached the state feature request, which is the current state to test in this case. In this state, we observe the next packet that is about to be sent, replace the field values with the values from the meta CA row, and send the altered packet to the target device. After that, the tool continues to send normal packets until the peripheral disconnects, either through reaching the disconnect state or the target device becomes unresponsive or the target device resets due to some errors. The oracle of the Greyhound fuzzer is very complex. It checks not only for crashes and unavailability, but also if a device under test sends valid responses after receiving an invalid packet. Additionally, it also checks if packets arrive in the correct state or if the test devices answer the packet that should not be accepted, answer to packets that should not be accepted in the current state, which in these cases the authors called anomalies. In our experiments, this actually led to a large number of false positives, which is why we decided to implement our own oracles to check for crashes. We monitor serial output of the target device and check for the occurrence of core dumps and stack traces. To check for availability issues, we monitor if the target device is still sending packets. If this is not the case for at least 2 seconds, we mark the test as failed. The simplification reduces the amount of false positives a lot, but it also has a drawback that the oracles can't detect anomalies or more complex issues like insufficient secure encryption keys or something like this. So our test setup consists of 2 NRF 52840 dongles that have been flashed with the custom firmware that was implemented by the Greyhound developers. One is used for sending and transmitting packets and to the target microcontroller, while the other is used for the availability oracle to monitor BLE traffic to see if the target is still responsive. The separate sniffer dongle was necessary because the communication dongle sometimes became unresponsive in an unpredictable manner, which would then lead to incorrect oracle results. Both dongles are plugged into the laptop that is running our CST tool, and for logging the test results, we use the MongoDB database. Because of the amount of time it takes our tool to test a single device, we replicated the setup 4 times so we can test 4 microcontrollers in parallel. In total, we tested 10 different microcontrollers from 10 different vendors, and the firmware versions and sample applications that have been used are given here in this table. We also tested some devices with firmware versions that were previously tested by the Greyhound fuzzer. The sample applications are included in the SDKs that the vendors provide and represent simple devices that expose 1 or more services. Here we see an overview of our results. As we can see, most issues occurred in the initiating state, which is most likely because a lot of connection parameters are negotiated in the state, which makes this interaction especially complex. All in all, all issues we found were actually triggered by only a single parameter, which is given here in this table. After analyzing the errors in more detail, we categorized them in 4 different categories. TO, which stands for timeout, means that the device became unresponsive for a longer period of time, but managed to recover by itself after at most 2 minutes. URWF describes cases in which the target became unresponsive until it was manually reset, but the problem could be fixed by adding code to the example application. URN means that the device became unresponsive and a manual reset was needed to recover the functionality. And finally, the dump category summarizes cases in which the target produced a core dump. So the core dump would suggest some memory corruption or some more severe issue, while the others are simply DDoS attacks or the things that could be fixed can also be fixed in the application. So to compare our results, we also tested our suite of test devices using the original version of the Greyhound fuzzer. Here we see the comparison between the 2 with Greyhound standing for Greyhound and GH standing for Greyhound, and CST being our CST approach. As we can see here, the CST tool was most of the time able to detect more issues than the Greyhound fuzzer, but also executed fewer tests while at the same time taking the same amount of time. Also, our tool was not able to detect anomalies, as already mentioned, which is why the column is empty here. Here we see a short summary of the results. In total, the Greyhound fuzzer was able to execute nearly 4 times the amount of tests, but found 2 issues less than the CST approach. Both methods found most of the issues in early stages of the testing. The fuzzer found all of the issues in the first 600 iterations, while the CST tool found most of the issues in the initiating state. We disclosed the issues to the vendors, and Espressive acknowledged the bug and fixed it and also paid us a bug bounty. Realtek asked for more details in the beginning, but then stopped responding after we sent them more information, while the other vendors did not respond at all. So now a quick summary of what was presented. First, we have shown that CST can be applied to the testing of BLE protocol. All the issues we found were triggered by a single parameter, and we have seen that despite our current approach being relatively simple, it is still capable of finding many issues. As always, testing is difficult to find the right balance between coverage and execution time, and also to figure out which parts of the target are most likely to contain flaws. In general, CST is more consistent in finding errors than traditional fuzzing, but requires more work to create the initial models. So thank you very much. I hope you liked the talk. Are there any questions?
You sure did like it. Thank our speaker.